right, so we're going to kind of wrap up this week with the next to last section of this unit. There will be one more next week. We've been talking about the families, and we talked about the hydrogen. You know how hydrogen's on its own. It's on its own little family. Then you have the alkali metals, which are the most reactive metals because of their valence electrons. And we talked about reactivity. Right. So reactivity is an important vocab term for you to understand and what it means when we say it's reactive or it's non-reactive. Right. So we will be describing elements on the periodic table based off their reactivity. So elements that are reactive bond easily with other elements to make compounds, meaning that they want to interact with other atoms. They want to become full. They want to become stable. Certain elements on the periodic table, with certain amount of valence electrons are very reactive. They're unstable. And the only way they're going to be stable is to gain or lose electrons or share electrons. And that's where we see chemical bonds and compounds come into play. Right? So that when we talk about reactivity, we're talking about the amount or the willingness or lack thereof of an atom wanting to bond some shape, form, or fashion to another atom in order to become stable. All right, so a great example is going to be sodium Na and chlorine Cl. Okay, um, sodium chloride together is the name of table salt. Okay, sodium has one valence electron. Chlorine has 7 valence electrons. Okay, um, so chlorine needs one valence electron to have 8. With the exception of the first energy level, each energy level is going to hold 8 electrons. For elementary purposes, when we're talking about being full with valence electrons, the magic number is 8, or the rule of 8, the octet rule. Okay, the only exception is for like hydrogen has this one energy level. First energy level hold 2, and then it's 8, 8, 8, so on and so forth. So if I'm sodium, or if you're sodium, and you're wanting to become stable, right? You have 2 options to become stable. You have one valence electron. You need 8 in that outer shell. Okay. So you have 1. You can either give up that 1 or go out and find 7 to take. Now remember, naturally nature is going to be lazy. What I mean by that is nature wants to achieve a goal the fastest and the most efficient way possible. Okay. It doesn't want to put forth a lot of work. What that means is it's going to take a lot of work to go out and find 7 electrons to make that outer shell full. Whereas if I'm sodium, I can just give up that 1 electron, and then the orbital inside of that 1 is going to be full. There's 8. 1, 2, 3, 4, 5, 6, 7, 8. If we look at chlorine, if I'm chlorine, I've got 7 valence electrons. So I have 2 choices. I either give up 7 or I go out and find 1 to become full or have my 8 or meet the octet rule. This is why the alkali metals and I think it's a halogen group, um, they combine so well together. Okay, the alkali metals want to give up 1, and the chlorine family wants to take 1. Okay, and they create compounds like table salt NaCl. And that's what this is saying throughout these slides. Excuse me. All right, so moving on to the next family, going over one column. This is known as the alkaline earth metals. They are never found uncombined in nature. What I mean by that is they are never found in their pure elemental form in nature. They're always bonded to something else. They have 2 valence electrons. And some common elements in this family are magnesium, calcium, calcium being the big one. So they have 2 valence electrons, and that's where they differ between the alkaline metals and the alkaline earth metals. Okay, alkaline earth metals are not as reactive as the alkaline metals, but they are still reactive. They are still wanting to become full. All right, then we go into this big block here in the middle of the periodic table, which is going to be known as the transition metals or the transition elements. So the transition elements include the elements in the B family. These are the metals that you're probably most familiar with, like copper, tin, zinc, iron, nickel, gold, and silver. They are good conductors of heat and electricity, and these elements are typically unreactive. They'll react, but they're not very eager to react. And even there's some what we call noble metals within the transition elements, like gold, for instance. Gold is not necessarily full when it comes to valence electron standards, but it doesn't like to react with other things. It will, but it doesn't like to. We see that here with these metals. Okay? Not a lot of reacting going on, not a lot of compounds being made, but it is possible. All right, so the compounds of transition metals are usually brightly colored and are often used to color paints. Transition elements have one or two valence electrons, which they lose when they form bonds with other atoms. Some transition elements can lose electrons in the next to outermost level. That's upper level stuff, and when we get back in person, we will talk about it and I'll show you. We have some atoms and elements in certain families that the outermost shell is not where electrons are going to be added or taken away. Sometimes it's underneath. And that's where things get very interesting and tricky as far as understanding reactivity. Another great example, we'll talk about it here in a minute, is another family called the rare earth metals. They don't follow the typical rules when it comes to valence electrons. Transition elements have properties that are similar to one another and to other metals, but their properties do not fit in with those of the other family. Many transition metals combine chemically with oxygen to form compounds called oxides. All right, so then we're moving over to the boron family. So we're moving one column over from the transition metals. So the boron family is named after the element and the first element in the family. So this top square up here is boron. Atoms in this family have 3 valence electrons, and the family includes a metalloid boron, and the rest are metals. This family includes the most abundant metal in the Earth's crust, which is aluminum. Okay, so the thing I hope you're starting to pick up on here, with the exemption of the transition metals, okay, they kind of throw things off. This column, first column, has 1 transition metal, or transition, 1 valence electron. This column, the alkaline earths, have 2 valence electrons. Skipping the transition metals, now we're at the boron family. They have 3 valence electrons. And we move on, if pattern holds true, then this column will have 4 valence electrons, so on and so forth. Which next is carbon family, an extremely important family, and carbon's extremely important. So atoms in this family have 4 valence electrons. This family includes a non-metal carbon. It also includes a metalloid, and the rest are going to be metals. The element carbon is called the basics of life, and there's an entire branch of chemistry devoted to carbon compounds called organic chemistry. Carbon is the backbone of living things. Carbon's it's called tetravalence, which means it has 4 valence electrons. That gives carbon the flexibility to bond to a lot of things and to make long chains. And carbon also has the ability to bond to itself. And that is what gives life, so to speak. Then we move into the nitrogen family, which is 1 over. So nitrogen family is named after the element that makes up 70% of our atmosphere. So 70% or 78% of the gas we breathe is nitrogen. This family includes nonmetals, metalloids, and metals. And the atoms in this family are going to have 5 valence electrons, and they tend to share electrons when they bond. Okay, so they're not typically going to make, or they don't like to make ionic bonds, which means they gain or lose electrons. They like covalent bonds. Covalent means they share valence electrons. Some other elements in this family are phosphorus, which are very important, or is found in living things, arsenic, antimony, and bismuth. Bismuth is used in carbonated drinks. We move into the oxygen family. Excuse me. Oxygen family has 6 valence electrons. Most elements in this family share electrons with forming compounds. Oxygen is the most abundant element in the Earth's crust. It is extremely active or extremely reactive and combines with almost all elements. Then we move into the halogen family. Very interesting family. Okay, so if you think back to chlorine, okay, we talked about chlorine, it had 7 valence electrons. It needs 1 more. So the halogen family is going to be extremely reactive. They are on the hunt constantly for 1 electron. Chlorine will take an electron from anything, particularly, chlorine. Pure elemental chlorine is going to be a gas. It's a poison. And if it gets in your lungs, it will take a hydrogen from the water in your lungs to create hydrochloric acid and eat your lungs inside out. Okay, and that's just one example of how reactive it is. And the interesting thing with chlorine and sodium, if we go back to the alkali metals, pure elemental sodium will explode in the presence of water, much like a hand grenade. Pure elemental chlorine is a poisonous gas. You put those two together, two very reactive elements, and they calm down and they create this element or this compound that we have to have to live, which is salt. Okay. If you didn't know it, you would not think anything about table salt, sodium chloride, is dangerous, except if you have too much of it. But the two things that are put together to make sodium chloride are extremely dangerous when they're by themselves. So when we talk about becoming full, becoming stable, elements coming together to become stable, this is a prime example of what we're talking about. Sodium by itself, not very stable, extremely reactive. Chlorine by itself, not very stable, extremely reactive. Put them together, they create an ionic compound. Now they are really stable and they're not very reactive and they're not dangerous. And then the last family is going to be the noble gases. And we call them noble gases for a very particular reason. They're called noble gases because they do not react with other elements. They do not they do not like to socialize with all these other elements on the periodic table. They're full. Their outer shell has 8 electrons. They don't need any more. Okay. Um, so this is the most unreactive family on the periodic table. So the reason they're called noble, if you think about, the people of nobility, they don't like to, or they didn't like to hang out and conversate with the riffraff or the common folk. They like to be off by themselves. Noble gases are very similar. Okay, they're not going to mingle with the rest of the periodic table. All right, so down here at the bottom of the periodic table, you have where some new elements are being added instead of being stuck in here, making the transition or the transition elements longer. Kind of stick it down here at the bottom. You have what's called rare earth metals, and they're not rare earth. They're not called rare because they're hard to find. They're called rare because they're hard to work with. Okay, what we mean by being hard to work with is every one of their outer shells is going to be the same. It's full. Their valence electron or their reactivity or their fingerprint of electrons is found on the level inside the outer level. It's really hard to work with these elements. It's really hard to figure out which of the ones you have. But there are some very important elements here in the rare earth metals. One of them being neodymium. Okay, neodymium is what is a very strong magnet which drives cell phones, computers, laptops, also used in other type of fishing enterprises to keep certain fish away from fishing hooks. Um, so it's extremely important, especially with technology advancements that are happening. But it's extremely hard to find, and it's extremely hard to work with once it's found. There's a lot of rare earth metals in the crust, but the problem is how expensive it is to work with these elements. How expensive it is to decide which of the rare earth metals you have. It's not cheap right now, and we'll watch a video at some point over this, and it's really very interesting. All right, so that's where we'll end today. Be sure you complete the video form, and this also kind of wraps up our week. If you have questions, let me know. Thank you.